Alright, we're going to talk about section 8.1, confidence intervals intro. So the question that I'm posing to you is, what was the mean score for Mr. Upjohn's AP Stats students on the final exam? So first of all, is that number a statistic or parameter? It's a statistic because it comes from a sample. Because the whole population would be all of the AP students at Lockport Township. Although it could just be our population as well, depending on how you classify it. However, number 2 says that we're using all AP Stats exams in the school. So what kind of sampling? It's convenience. It's also a cluster. So and or however you want to put it, both would be fine. And then we're going to make a guess as to the mean score for the final exam, and we'll talk about how we get a good guess versus a bad guess and whatnot. Now, when we talk about what a confidence interval is an educated guess of a number. This is an educated guess of a parameter of something from a population, because we can't find the whole thing of a population. So confidence interval is just an educated guess of the parameter. Now, we don't just guess willy-nilly. We have to have a starting point. Our starting point is the point estimator, or the point estimate. A point estimator is a statistic that provides an estimate of a population parameter. So our parameters would be mu for mean, p for proportion, sigma for standard deviation, and sigma squared for variance. The statistic, or the point estimator, would be x bar, p hat, s, and s squared respectively for each one of those. So if I want to make a guess about mu, I'm going to use x bar. If I want to make a guess about p, I'm going to use p hat, and so on and so forth. Now the confidence level gives us an interval of possible values for the parameter. We do get an interval, and it's in the form of point estimate, our guess, plus or minus the margin of error, plus or minus some numbers, so we kind of have wiggle room. The difference between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. Now the margin of error is the second part. It's made up of 2 different things, and we'll look at that later. The confidence level gives the overall success rate of the method for calculating the confidence interval. So it kind of tells us how good our guess is. So let's do some. The mean score for your exams, my 2 classes, was a 71.61, which again I think is pretty good. Standard deviation is, well, the standard deviation divided by the square root of n, because this is a sample. So we have to do the sampling distribution. So 12.12 was the standard deviation from my 2nd and 3rd period classes divided by 57 people. So we get a standard deviation of 1.61. It's a lot lower than what it originally was because we're taking samples instead of just one person individually. Now, what did we assume to find the mean and standard deviation? Well, we assumed that 57 is less than 10% of all AP Stats students, which is not true. But we're going to continue anyways, and this is a good thing to come up. This is going to happen a lot. Just because it doesn't meet the conditions we need doesn't mean we just stop and we give up. We say, hey, it's not true or we can't prove it, but we're going to continue anyways. So what is the 95% confidence interval about the true mean of all AP Stats final exams based on our data? Well, we make our normal distribution. Why is it normal? Because, I guess that's getting at number 5. What did we assume to do that? The sample distribution of the mean was normal, and because n equals 57, which is greater than 30, it is true by the central limit theorem. So we have our mean in the middle, our point estimate, 71.61, and then we add 1.61 3 times, and we subtract it 3 times to get our values. And remember that this is our empirical rule, that between those two is 68%. Now, what are we really looking for? we're looking for all of that. We want between 2 standard deviations, and it's 95%. The last number is our 99.7%. Just a quick review of our empirical rule, or our 68, 95, 99.7 rule. So what is the 95% confidence interval? Well, we base it around our point estimate, our mean, 71.61, and 95% is 2 standard deviations either way. So I added 1.61 twice to get 74.83. I subtracted it twice to get 68.39. So my confidence interval is 68.39, 74.83. That's my guess. I think the true proportion of the mean based on our data is in here. So how do we interpret that? What does that mean? Well, we are 95% confident that the true mean of all AP Stat final exam scores are between 68.39 and 74.83 based on our data, just based on what we have. Somebody could have a different sample. Mr. Lorkowitz's AP Stats classes could have a different mean, and maybe the proportion is different. But based on what we have, these are our best guesses. And again, it's of all AP Stat final exams, and I guess we're talking about at this school. Interpret the confidence level. If we take many samples of the same size, that's the important part, from this population, about 95% of them will result in an interval that includes the actual mean of all AP Stats final exam scores. Now again, we don't know what that what the actual mean is of the population. We can't know. We're guessing based off of our sample. But if we keep taking samples, about 95% of them should include whatever it is. So we can, I guess, kind of narrow it down. Notice it does not say that we are 95% sure that the interval includes our mean. No, it's either in or it's out. It can't be 95%. It's our level of confidence that it's in there, or it's the number of samples that would have it in there based off of that. So population distribution and sampling distribution, the population is a smaller one here. Sampling distribution is a bigger one, so compare and contrast. The same, well, the area under the curve is 1. I guess they're both normal as well. What's different? Well, the population distribution is more spread out because it has a bigger standard deviation. Or, if you want to think about it this way, the sampling distribution has a smaller standard deviation, and we saw that on the first page. So it's less spread out and a little bit taller instead of wider. All right, and then we're gonna work here on our applet to look at the difference of the different confidence levels and the sample size and the percent hit, or the percent of intervals that actually have our mean. So we're looking here. And just play around with it, fill in the table. I want to show you what it's doing. If we take a sample, so we took a sample of 20, here are our sample 20 points from our population, the flatter one, and then we found the mean. Well, the mean is this number here, whatever that is. And then we did an interval, so we went our margin of error to the left and to the right. So this whole line is our confidence interval. And it includes our true proportion, or our true mean, sorry, right here. So it's 100% hit. Now if we take a little over 100, with 95% confidence level, well, we should have about 95% have the interval. Well, we have 97%, because we just have this one guy that the interval's a lot lower. We had a very low mean or sample statistic here. And you can see as the confidence interval grows, or as we're more confident, the intervals actually get bigger because our guess is not as good, not as accurate, but we're more sure that the real mean's in there. And then the opposite happens if we go this way. Now the same thing would happen if we take a bigger sample size. notice, even if we just take one sample, the mean is pretty close to the mean, and that's what we saw with sampling distributions. So if we're supposed to have a 93% confidence level, we have 91% that hit, and if we want to have more that hit, we increase our confidence, and that makes our intervals bigger. So that's what we want to do. Now, quiz me. So set the sample size to 50 and the confidence level to 80, click the sample 25, blah, blah, blah. As the confidence level rises, the confidence intervals in the graph get wider, while the percent hit, the number of samples whose intervals include the true proportion, grow larger. And that's what we were just talking about. The next question, as the sample size increases, the confidence intervals in the graph narrow because we're getting a little bit more specific, so our intervals can be smaller, and the percent hit stays the same because our confidence level didn't change. Now, based on our observations, is a 95% confidence interval calculated from a sample of 200 observations more likely, less likely, or equally likely to include the true population mean than a sample of 10 observations? Well, a 95% confidence interval is constructed specifically so there's a 95% chance that the interval includes the true population. So that means that no matter if we don't change the confidence interval, we're going to have the same number that include the true population mean. And that's what it says. And I got 10 out of 10. So, what are the two major factors that affect the size of the confidence interval? The confidence level, how sure we are, and the sample size, how many we're taking at a time. So what happens to the confidence interval when you increase the level of the confidence? Well, if you're more confident, the interval is going to get bigger. It's kind of a worse answer, a worse guess. It's a bigger range. And then the opposite is true as well. So they'll go in the same direction. Higher confidence, bigger interval. Now it's the opposite for our sample size. The bigger the sample size, the smaller the confidence interval because we're more sure. We're narrowed down our choices a little bit. And then the opposite is true for if n is decreased. What else changes when you change the sample size? Well, when you change the sample size, since we find our standard deviation by sigma divided by the standard square root of n, then standard deviation also changes. It goes the opposite of our sample size, which is why those increase, and we'll get more into that as we go. Now, a confidence interval. Now we can break it up a little bit more. It's a statistic plus or minus the critical value times the standard deviation of the statistic. This is the formula that's on your formula sheet for the AP test. So you need to know what the statistic might be, whether it's x bar, p hat, s, or s squared. Critical value we'll talk more about next week. And standard deviation of the statistic, well, we already know. It's either what we did, well, it's what we did in chapter 7. The square root of p times 1 minus p over n, or the square root of sigma, or sigma over the square root of n. Sampling distribution or sample proportion. So, and the margin of error is, supposed to be those two parts together. That's our plus or minus. The Gallup poll asked a random sample of 100 U.S. adults, would you like to lose weight? And no, don't anyone be laughing at the fact that I picked this question. Based on this poll, the 95% confidence interval for the population proportion P of U.S. adults is 0.56 to 0.62. So interpret the confidence interval. We are 95% confident the true proportion of all U.S. adults who like to lose weight is between 0.56 and 0.62 based on our data. Notice some key things here. It's of all. That's not going to work. It's of all U.S. adults. And it's based on our data. Because again, somebody could take a different poll, take a poll in Alaska, and maybe they don't want to lose weight because they need the weight for warmth. I don't know. Interpret the confidence interval. If we take many samples of the same size from the population, 95%, because that's our confidence level, of them result in an interval that includes a true proportion of U.S. adults that would like to lose weight. So our answers are going to be long, but they need to be written out. Same size. Many samples. Includes the true proportion. And then we got to say what the population is of U.S. adults that would like to lose weight. What is the point estimate for this interval? Well, remember how a confidence interval is built. It's our statistic, or our point estimate, plus or minus our margin of error. So, the middle of our interval, the middle of 0.56 and 0.62 is our point estimate, is our p hat in this case. P hat estimates p. So, we add those two up and divide by 2 to find the average of the middle. So p hat is 0.59. What is the standard deviation? Well, this is what we did last semester. The standard deviation of sampling distribution of our proportion here is, we're going to use p hat because we don't have p, is 0.59 times the complement, 0.41, divided by 100 because that's our sample size, so our standard deviation is 0.049. So it's just like what we did last semester. Clearly 100 is less than 10% of all U.S. adults, so it does work here. What is the margin of error? Well, how much do we go plus and minus from the middle? Well, 0.62 minus 0.59, the middle, or our p hat, or our p hat minus the lower limit. Either way, we get 0.03, so our margin of error is within plus or minus 0.03. What is the critical value? Well, now we need to work backwards. Remember, up here, the margin of error is the critical value times the standard deviation. Well, the margin of error is 0.03. Standard deviation is 0.049. We found that up here. Critical value is what we don't know, so we divide 0.03 by 0.049. We get 0.6122. That is our critical value, and we'll talk more about our critical value next week when we do more with actually finding confidence intervals.